call an alternating series. And so this one is kind of a nice deal because if we have an alternating series, sometimes that is what will allow the convergence as opposed to like just a normal series that won't converge because it doesn't drop to zero quick enough. And then as soon as we alternate the terms, meaning we add, then subtract, and then add and subtract, that will help us get to that kind of converging component. So this is what an alternating series will look like. Is it will have some sort of -1 to the n. It doesn't have to always be something that looks like that, but it's whatever would make your terms go plus, minus, plus, minus. Or -1 to the n plus 1 power, that would be like minus, plus, minus, plus, that sort of thing. So it will converge if the following two conditions are met, and we have to write these out so that we can't just like think these thoughts. We have to write them out as part of that justification. So first it has to like kind of make sure that the n terms do approach zero, right? So we would take the limit as n goes to infinity, and then that is just making sure that those n terms will go to zero. So if they don't go to zero, then it's going to diverge, right, by the nth term test. So we need to make sure the n terms go to zero. And then we also need to make sure that the terms get smaller. So that your nth plus 1 term has to be less than or equal to the nth term. And so we can determine that the series is decreasing just most of the time. It'd just be by logic, right? Like if the denominator is bigger, then the fraction is smaller. We can also graph it if we want to. We can also make sure it's decreasing. Oh, this is a good one. If the derivative is negative, right? So we know that if prime is less than 0, then f would be decreasing. A good chapter 3 review, okay? So if both of these conditions are met, then we can say that our series would converge. So just to kind of, maybe give you some thoughts to like, well, what the heck? What's that all about? So if we had, for example, like our harmonic p series, so 1 over n to the first, like that would be, 1 plus 1/2 plus a third plus a fourth plus so on, and then the n terms would approach 0. Right. And so we know that this series diverges, right? So this is a series that diverges. So even though the n terms go to 0, it just doesn't do it quick enough. So these front terms would add up to some sort of infinity, right? So this would approach infinity before it got to those 0 terms. And why is that? So just a reminder, it's because our rate of growth is not big enough, right? The difference between 2 and 3 is only 1, right? 3 and 4 is still 1. 4 and 5 is still 1. So there's not an increase in that rate. And so because there's not an increase in that rate, it won't drop to 0 quick enough. And so what we look at is, well, hey, what if we alternated it, right? What if we alternated it? So what if all of a sudden we're like, hey, let's go -1 to the n. So we would get like negative plus, and then actually, I don't know, where are we starting at? N equals 1. All right, let's go n plus 1. So I don't have to start with a negative. So like if that was a plus, and then now this will switch to every other term. So now this would be minus, and then we would add, and then we would subtract, and then when we add. So what's happening here is instead of us just going 1 plus 1/2, which is 1.5, plus a third, plus a fourth, we're saying, well, what if we have 1, and then let's subtract 1/2. That makes the number smaller. And then we add a third, which makes it a little bigger. And then we subtract a fourth, which takes a little away. So because we're not just adding a bunch of terms, we're also taking away value, then it will drop to 0 quick enough. And this will add up to some sort of, finite value because we're subtracting, not just adding. And so that's kind of what that alternating series component does for us, is it says, all right, well, let's just take a few away and let's see if that will make it converge versus diverge. Okay. All right. So how do we use an alternating series? Well, first, you need to look and say, well, is it alternating? So let's make sure that we always know that we have an alternating series before we try to use that test. Okay. So so when I look at this, so I'm not going to have this per se as a test, but I want to make sure that I'm recognizing it as an alternating series. So this would be -1 to the n over 1 over the square root of n. So that would be to the power of 1/2. So this piece right here is the part that makes it alternate, right? Meaning if I were to let n equal 1, I would get -1 to the first, which is negative, and then n equals 2, it would square it, make it positive. So anytime n is an odd number, it would be negative, and anytime n was an even number, my term would be positive. So that is the portion that alternates. So yes, it is alternating. Okay, so step 1 though, is we want to write out what AN is. So not the piece that alternates it, but what is the piece that generates the terms. Okay, so we would write out AN. So for this particular problem, AN would be 1 over the square root of n, or n to the 1/2. So I know under normal circumstances, so this would not be part of our like actually doing the math, but under normal circumstances, this would be a p-series equal to 1, which is less than 1, which would diverge, right? It's just not dropping to 0 quick enough because that would be concave down. I have a increasing function that is at a decreasing rate. So under normal circumstances, this would diverge. So let's see if we take half the terms and make them negative, if that would be enough to get it to now converge all of a sudden. So then we're going to do step 1, right? So we're going to do this part right here, and we will take the limit to infinity, right? And see if it meets condition 1. And again, this is something we have to write out. We can't just think these thoughts. Okay, so step 1, we would take the limit of 1 over n to the 1/2 as n approaches infinity. So the denominator is going to infinity. So then the whole fraction is going to 0. So far, so good. So if it wasn't 0, it automatically diverges because of the nth term test. Okay, so then once we take the limit, now we are going to replace n with n plus 1, and that will find me my nth plus 1 term. And then we're going to, once we do that, then we are going to check the inequality. I don't know if it's recording, but there's like work going on outside my window and it's really loud in my ear. Hopefully it's not loud in your ear. Okay, so let's go ahead and we're going to find, as soon as I can get my eraser to click off. There we go. So I'm going to find AN plus 1 by replacing n with n plus 1. Okay, and then I'm going to compare that inequality. And I'm going to go ahead and let me just write, this is like justification 1 up here, and then now I'm going to look for justification 2. So I have my nth plus 1 term, so that would be 1 over the square root of n plus 1, or to the power of 1/2. And then I'm going to compare that to 1 over the square root of n. And so right here, I know that n plus 1 is bigger, right? So I have a bigger denominator, so I have a smaller fraction, right? Bigger denominator, so this denominator is larger. And so that means that whole fraction then is going to be smaller. And so that is also, so that's the second piece of the alternating series. And so because both of those are true, then I can make the conclusion that that alternating series converges. So if it did not have the alternating piece, right? So if this alternating piece was not here, this would be a series, right? That would have been an infinite series that diverged because that p-series states that, right? So because now half the terms are minus, it's going to allow that those first finite terms to add up to a finite value. And not add up to infinity before it hits those tail end terms approaching 0. All right, so that, and then that's all we would have to do, right? Okay, so let's take a look at the alternating series remainder. And we will have another remainder later on as well at the end of this chapter, so try to keep like the two remainders separate from each other. But so right now though, we just have the alternating series. So if we have a convergent alternating series, okay, so we have an alternating series and we know it converges, okay, then the absolute value of the remainder, okay, in approximating the sum has to be less than or equal to the first neglected term, okay? So this is my actual sum of my alternating series, right? Like what it would sum up to if it converged. This would be my approximated sum, right? Which is adding up, however many terms. And they're saying, so like I have this approximated versus the actual. So the difference between those two is called our remainder, right? So like, if the actual sum, right, added up to 12, but the nth partial sum added to 11.5. So what would be the remainder? The remainder would be 0.5, right? Because I'm off by like 1/2. Like that's what like all of that portion is saying. And they're saying that, well, we're never going to really know, like not never really know, but this right here, this is hard to find. Like to figure out like what does the sum actually equal? That's really hard to find. This is easy to find because if I want to know the third partial sum, I add up 3 numbers, easy peasy. And so if this is hard to find, this is easy to find, then this would also be hard to find, right? To know exactly how far off I am. Because if I don't know what this number is, if this number right here is a big old fat question mark, then this would have to be a big old fat question mark as well, right? Because if I don't know this, I'm certainly not gonna be able to subtract it to find my remainder. So what we say is we're like, okay, well, I don't really know exactly what this is equal to, but I at least know it has to be smaller than the first term I didn't use. And that's what they mean by the first neglected term. So if I used, say, the third partial sum to find 11.5, then the fourth term that I just found, it helps me at least get a ballpark of what the remainder is, right? And I know the remainder has to be smaller than or equal to that fourth term I didn't use. So that's kind of the gist. So hopefully that makes sense. All right, so let's go ahead and take a look at this problem here. So this one right here wants me to approximate the sum of the series by its first 6 terms and then find the error. So the first thing I'm going to do is just write out those first 6 terms, like that's going to be my first step. So I'm going to just let n equal 1, right? Start with 1. So put 1 in for here. So that would be negative 1 squared over 1 factorial. And then plus, and then now I'm just going to keep substituting the numbers in. And then, so that would give me negative 1 cubed, and then 1 over 2 factorial, and then substitute. Wow, 6 terms is a lot. What was I thinking about the first 3 terms, people? Okay, and then let's go ahead and substitute in n equals 3. So then we'll get negative 1 to the 3 plus 1, so that would be 4 over 1 over 3 factorial, and so on. Okay, so let me write this out. Let me do a little arithmetic. So negative 1 squared is 1, and then 1 over 1 is 1. And then negative 1 cubed is minus, and then 1 over 2 factorial would be 2. And then negative 1 to the 4th would be plus, and then I would have 1 over 3 factorial, which is not 1/2. 1 over 3 factorial, which would be 3 times 2, so 6. And so on, right? So the next term would be minus. So that would be what that one is equal to. All right, so we want to approximate the sum of the series by the first 3 terms. So then I'm going to find my third partial sum. So that would be 1 minus 1/2 plus 1/6. And so what would that be? That would be 2 over 2, so that'd be 1/2, 3/6, so 4/6, so 2/3. Let's go with 2/3. So then what I am suggesting is that, that's not very many terms that I added together, so it's probably a terrible approximation, yeah? So, but I am saying that if I were to find the sum of this particular series, like whatever this is equal to, it certainly is not 2/3, right? But I'm saying that I'm approximating it with the third partial sum to say that it's about 2/3. So then my question is, well, how close are you? Like, how close is that approximation? And so how can I find that? So then and then it says to find the error. So how far off am I? So then I would find that the remainder, right? So the remainder of my third partial sum, like what I just found, has to be less than or equal to the first term I didn't use. The first term I didn't use. So, well, what was the first term I didn't use? I didn't use this one right here for when n was equal to 4, right? Because this was n equals 1, n equals 2, n equals 3. So my remainder has to be less than or equal to this first term I didn't use for when n was equal to 4. And so then that would be when n is equal to 4, negative, well, it's absolute value, so I don't need that, do I? So let me erase that. Okay, so because it's absolute value, that piece right here is just giving me the plus or the minus, so this piece is not going to matter for that. So it would be less than or equal to 1 over n factorial, which is 4 factorial. So then what is that? 24, right? Yeah, 1 over 24. So how far off am I from my sum? I'm actually pretty darn close, right? So 2/3 is what I got by just doing the third partial sum, whereas the actual, oops, no subscript there. Whereas the actual partial sum then has to be, somewhere in the range of 2/3 plus or minus 1/24, right? Because that's my remainder. So the actual sum has to kind of land in that value. And there is the alternating series remainder. All right, then the last little piece here is our absolute convergence. Like, what does that mean? And so this is just essentially saying that if you get rid of all of those plus or minuses and you have your series that converges, so it doesn't need the pluses and the minus to converge, then the alternating piece also has to converge. Okay, so what they're saying is, so if you had, say, 1 over n squared, so 1 plus, 1/4 plus 1/9, and so on. So that converges, right? It doesn't need to alternate. And then if I make every other term negative, it's going to add up to a finite value a whole lot quicker, right? Because now I'm adding a little, taking a little, adding a little, taking a little. So then alternating it isn't going to all of a sudden make it diverge because I'm like adding and taking away. So I'm actually dropping to 0 quicker. I'm adding up to that finite value quicker. And so the alternating piece doesn't help it converge if it already converges. So that's what that's saying. Okay. So if it doesn't need to alternate, then to converge, then we call it absolute convergence. And then, so this is our definition of absolute and what we call conditional convergence. Okay. So if our series is absolutely convergent, then the absolute value converges as well. That's the definition. We call it conditionally convergent if the alternating piece does converge, but if we take away the alternating piece and it diverges, then we call it conditionally convergent. So that would be like what I talked about on the front side. So like if we have, so the absolute value piece of it, so 1 over 1 plus 1 over 2 plus 1 over 3, so that harmonic p series. So we know this diverges. But if we make every other term negative, then it converges. So we call it conditionally convergence because we're going to add a little, take a little, add a little, take a little. But if they were all positive and we tried to add up to a finite value before we hit those zeros, it just would not happen and it would diverge. Okay, so when they're asking us to determine whether our series converges conditionally or absolutely, or just does it diverge, like, they're just asking, like, does it have to alternate in order for it to converge? And so there's like a couple of different ways that you can do this particular process. So I'm just going to show you one way, but there is, you can like flip the order in which I do things, I guess is what I want to say. So I always just test to see if the absolute value piece converges or not. Okay, so I always test for convergence on the non-alternating component. So that would be so I just test first, like maybe it just diverges and that would be great. And then I could be done. So that's what I always do, is I just test for like the absolute value piece. And then if it diverges, I'm done with the problem, because then everything's going to, well, I'm not done with the problem, but it kind of falls into place a little bit better. And then if it does converge in the absolute value sense, then I know the alternating piece will converge as well. So I kind of get more information in my mind, like which direction do I head? Can I stop, or do I need to keep going? I guess that's what I want to say. So, but again, you don't need to do it this way. This is just the way I do it. Okay. So I'm going to go ahead and test for that convergence. So I'm going to look at, so this is a part that makes it alternate, right? Plus and minus. So then I'm going to test just for 1 over the natural log of n. And so if this does converge, then I would say it is absolutely convergent, and then I'm finished. If it diverges, then I test to see, okay, what if I make half the terms negative, plus, minus, and then I do the alternating series test. Okay. So this is not a series that I know. So then I'm going to do a comparison test. So I'm going to say AN is my original, and then BN is some sort of basic. So I'm going to just compare it with 1 over n to the first, because the natural log is not land me in P or geometric. And so then I know for this one here, whoops, that Bn diverges because this is a P series, right? Or harmonic. And so P is equal to 1, which is not greater than 1, right? So it's less than or equal to 1 and greater than 0. And so then I know that is true. Okay, so then now if I do 1 over the natural log of n, oops, and then I want to compare that to 1 over n. So I'm going to do the comparison test. So I know that n is larger than the natural log of n, like that's something I know. And so because it has a larger denominator, that makes it a smaller fraction. If you aren't sure, look at your denominators, right? So what does a graph of n look like versus what does a graph of natural log of n look like? And so like that's like, so like in my brain, like that's kind of how I know is this is actually goes like that, but for greater than 2. So I know that n, is linear, which will always be above the natural log. I also know that natural log is one of the slowest growing graphs that we have, like, and the radicals as well. And so that's like another way that I know that. If you don't know it, graph it, write out a few terms, compare it. But that is what I do know. Okay, so then I know that Bn, which is the right-hand side, is smaller, right? So this one is smaller and it diverges. So if the smaller one diverges, the larger one has to diverge as well. So then therefore, I know that the absolute value of that is going to diverge, and that is by the direct comparison test. So if it converged, I would be done with the problem and say it absolutely converges, right? But unfortunately, or fortunately, I don't know which, it diverges. So then I have to test to see, well, what if I alternated it? Let me go back to that. And so if it converged, so if step 1 converged, you are done because it would converge absolutely, right? Because you took the absolute value. Absolutely. Okay. If step 1 diverges, then you're going to use the alternating series test. And then for that, you're checking to see if it's conditionally convergent. Okay, so let us go back to the original problem, which was -1 to the n over the natural log of n from 2 to infinity. Okay, so then the first thing I'm going to do is, so now I'm going to identify my AN again, because I want to, make sure that I know I'm looking at, a different test system here. And so alternating series, first thing we do is we take the limit to infinity. And so then I know that the natural log of n, so as the denominator is growing to infinity, then the whole fraction is going to approach 0. Excellent. In terms go to 0. Then the next thing I want to check is do the terms decrease. So do the terms decrease. So I'm going to take 1 over the natural log of the nth plus 1 term. So let me write that one up here. Replace n with n plus 1. Group it. And I want to compare that with 1 over the natural log of n. So is this denominator, this denominator is bigger than this denominator. So the bigger the denominator, the smaller the fraction. So the terms are decreasing. Excellent. And so because they are decreasing, then we can make a conclusion that the alternating series is conditionally convergent. Oops. And then why is that again? So that is because it has to alternate in order for the series to converge, because we showed up here that if it did not alternate, it diverged.